Hello, class. Welcome to the next section, chapter 9.4. Today we're going to talk about integration by partial fractions. So, if you've seen partial fractions before, then this will be review. If you've never seen partial fractions, then basically what we're doing is we're learning the method of partial fraction decomposition. So, partial fractions is a method of separating a single rational function, right? A function on top, function on bottom, generally parabola or polynomial, and we're going to turn that into a sum of smaller rational expressions. So we think about this as undoing the addition of two or several more rational expressions. The process is called partial fraction decomposition. Okay, so we have a rational function, which we call r of x, that is made up of a numerator function and a denominator function. Generally, for our purposes here, we're taking polynomials on top, polynomials on bottom. But anytime you have a function on top and a function on bottom, then it is a rational function. Okay. So first thing that we're going to do when we see a rational function that has polynomials in the numerator and denominator, we want to look at the degree of the numerator in comparison to the denominator. If my numerator has a higher degree polynomial, or if they're the same, then we want to use synthetic division or long division, depending on what we have for q. Otherwise, we can use partial fraction decomposition. So we use partial fraction whenever q is a higher degree than p. Any other time, we have to use long division or synthetic division, and we may end up having to do a partial fraction decomposition after that long division. Okay. So in order to separate a rational expression, we need to consider the different forms of Q, right? So partial fraction decomposition is really based off of what Q looks like in its factored form, okay? So there's four cases to consider for the form of Q. The first is that all of the factors are linear, so nothing more than degree one, and they're all different, right? They're all distinct, right? So this factors to a bunch of little binomial terms, and all of those binomial terms are linear, and none of them are the same. Okay. Second case is that some of those linear binomial factors are the same, right? So maybe you have a couple of x plus 2 squares or x plus 2s, right? So if I have two of them, I would square it. If I had 10 of them, it would be x plus 2 to the 10th would be a factor, right? So whenever I have factors of my linear binomial factors. Okay, so with multiplicity. The next case is that they're quadratic in nature, and that they're prime over the integers. And the fourth case is that they are binomial, that they are quadratics, and that they are prime, and that there's multiplicities of them. There's more than one of the same thing there. Right? So those are the four factors. All linear factors that are distinct, or linear factors that can have some multiplicities, and then prime quadratic factors, and then prime quadratic factors of multiplicity. So those are the four cases. So case one, distinct linear factors. So if we factor q and all of the factors are distinct and none of them are higher than degree one, a line, okay, meaning that I can factor to look something like this. So a1 times x plus b1, a2 times x plus b2. And again, this could be negative, so that's where the subtractions would come in here. But all of these things look different. None of them are the same. Okay. Then my rational function, when I decompose it through partial fraction decomposition, will look like this. Some constant on top of the first factor plus some constant on top of the second factor. And I do that for each factor present. Okay, so that's the first case. If one or multiple of these has multiplicity, so maybe there's like four of these, so this would be a fourth, a1 x plus b1 to the fourth power, right? So if there's four of these first terms, for instance, I would go to case two, right? Which is that for each linear factor that has multiplicity, I start to break it down in this form. Some constant over it, plus some constant over that same factor but squared. Some constant over the same factor but cubed, so forth and so forth until I get up to whatever that factor of k is, right? So if it's a 10th degree, I would break that one single 10th degree term down into 10 pieces. Okay? We'll do examples for all of these. So for right now, just kind of think about what I'm saying and taking in, and then when we do the examples, you'll kind of see how this works out. So if I have a single prime quadratic factor, so something degree 2, okay, then the factor for p of x over q of x has an expansion of ax plus b over that prime quadratic. Okay, so that single factor. So again, we can have mixes of all of these. I could have one that's distinct. Maybe the next one is a cube, and then maybe the next factor I have is quadratic and it's prime. I would do a little bit of all of these, right? So it's very possible that you have one partial fraction decomposition that you have to do for a rational function that has all four cases in the one problem. Okay, so again, these are not things that happen separate of one another. Generally happen with each other. So you have to be four cases every time you do a problem. So case 4 is that our prime quadratic factor has a multiplicity, right? A multiplicity of k. So if q can be broken down to a prime quadratic, then it looks like this. Again, we have a1x plus b1, some constant times x plus a different number. So each one of these will be different, and we just repeat that factor until we get up to k times. Okay, so very similar to what we do. So 1 and 3 kind of mirror each other. One's linear, one is for quadratics, and then case 2 and case 4 mirror each other, but they're for multiplicities of k. Now you might say, well, what happens if it was a third degree, a cubic that was prime? It would follow the same thing, right? It's just that instead of, right, so if you think about it for quadratic, you went down one, ax 1 degree down, ax plus b1. If this was a cubic, right, a third degree polynomial, well, then this would be a1 x squared plus b1 x plus c, right? You would just do the same thing, except that now it would be cubic on top, right? So it's kind of following a pattern if you haven't noticed, right? So you just extrapolate that pattern to the next set, which should not happen. You won't get any problems in this class, at least to have to give you a cubic, a prime cubic. So what is the process? Okay, if the degree of p of x is larger than q of x, then we're going to use long or synthetic division. So depending on the difference in the degree here, we either use long division or synthetic division. So otherwise we use synthetic division to, what do you call it, to factor this, right? So if q is larger than p, we could just go ahead and use synthetic division out of the gate, because then our only goal is to factor q, right? Otherwise, we're trying to do division here between p and q. If this doesn't hold, right? If q is a bigger degree, I don't have to divide them. I just need to factor q. Okay. And so synthetic division is the method that I teach. If you are not familiar with synthetic division, we will go over it very, very briefly here with an example, but I will not be um, going over too much. You can go to my pre-calculus video series. There's an entire chapter on factoring, or you can go to my Calculus 1 material. There's a review there of pre-calculus, and it goes into how to do irrational functions and polynomial functions. And in the polynomial functions section, it has synthetic division. Okay. Once we have either divided or factored q, then we want to rewrite my entire function based on the generic decomposition that I found using these like a1x plus b1s, or this a1x plus b1, a2x plus b2. So this little generic thing that we did, we would write that out so that we can set up step 4, which is to clear denominators, right? So I'm writing original R of X is equal to now this decomposition that I found. I'm going to clear denominators by multiplying both sides of the equal sign, the largest common multiple, um, so that I get rid of all the denominators. Then I'm going to equate the coefficients from that remaining equation that I have, and I form a system of linear equations. And then I have to solve the system of linear equations. So if you know how to use matrices, if your pre-calculus went over that with you, you can use matrices, right? That's the method I teach in my pre-calc. Again, you can go, you can look at the matrices section in order to get an idea of how to use matrices to solve something like that. Or you can solve it by hand, right? Plugging one equation into the other, trying to eliminate variables, which is fine, right? So um, once we do that and we solve our system, we rewrite our problem, but the values we found from solving the system, we can now substitute into these A1s and B1s and these smaller values that I have down here, okay, on both options, right? Whichever one of these 4 cases apply, then I'm going to substitute my values from 6 back into those cases. Then I have now decomposed my integrand, and then I can integrate, right? So let's go ahead and do an example. So we'll do a few examples that have a little bit of everything in them. So here I need to integrate x to the 5th plus x minus 1 over x cubed plus 1. If you notice, my numerator has a higher degree than my denominator. So that means I need to divide, right? So again, the numerator is higher than the denominator. So we're going to use division. Synthetic division only works if your denominator is a linear factor, meaning it has to be a binomial of degree 1. It has to be x plus 1, x minus 7, uh, x plus 2/3, 2x minus 3, right? Something like that. It can't be a squared or a cube on the bottom in order to use the synthetic division. So here we got to go old school and use long division of polynomials, which is just like regular division, but it sucks more because there's more things you have to remember. So we're going to go ahead and use our long division of polynomials. We're going to put our numerator on the inside, and notice I have placeholders here. It goes x to the 5th and then x, so I'm going to use a placeholder everywhere I'm missing a power of x, right? Again, I go over this in my Calculus 1 chapter 1 where we review the basic algebra stuff. So if you need to review anything, that's kind of where you would want to go, right? So I do talk about this there, but just to refresh you, we leave a placeholder, right? So make sure you're putting zeros where they're not, okay? I'm going to do the same thing with my denominator, right? I'm dividing the top by the number on bottom, just like a regular fraction, right? So I'm going to do the same thing. I'm going to keep my placeholders here so that when I do this long division, everything makes sense. So then I look at x cubed, okay? My biggest degree, my first term here, and I say, hey, how do I get x3 to be this number? Well, there's no number here, so I don't need a multiple of this. But in order to get from x cubed to x5, I need 2 x's. So I'm going to have x squared, okay? X squared. And I want to line that up with where the x squared would be, right? That's why they're placeholders here. So x squared times x cubed is x5. So now what I'm going to do is I'm going to multiply this times this entire thing, so really just these 2 terms, and I'm going to subtract it on the bottom. So x squared times x cubed is x5, x squared times 0, x squared times 0, x squared times 1. And I'm subtracting that from here. So instead of throwing this in the parentheses, I'm just going to distribute the parentheses and subtract everything. So this gets subtracted, this one, and this one straight ahead. This turns into 0, right? It's the same thing being subtracted. 0 minus 0 is 0. 0 minus 0 is 0. 0 minus x squared will give me a negative x squared. Okay? I drop everything else from that point on. Okay, So this is the next number I'm trying to evaluate. So then I say, hey, how do I go from x cubed into x squared? I don't. There's nothing for me to multiply times x cubed to get to x squared. It's a lower degree. I'm only trying to work upwards, right? I'm dividing here. So I'm done. So my answer is not my final answer, but this rational integrand turns into x squared plus my remainder over the number of things I'm dividing it into. Okay. So my integrand x5 plus x minus 1 over x plus 1 is equal to x squared minus my remainder, right? Because now my number that's left over is less than what I'm dividing by. So this is my remainder. You notice I changed the signs here because I pulled out a negative and I just said, let's subtract it. I don't like my first term being negative. So instead of saying positive, negative x squared plus x minus 1 and adding those two things, I just distribute the negative out. So it's a subtraction. You don't have to do that, but I myself prefer to do that. So now look what I have left over. If I want to integrate this, I got to integrate this. But now we still have a problem. I still have, once I distribute this integral sign, I still have a rational function, right? But notice this time, the numerator is less than the denominator. So now all I have to do is factor, okay? And so whenever you have a cubic, you'll always have at least one real factor. Um, so that's why we can always factor this once we get, to a cube of fourth degree. We should always be able to factor at least a little bit also. Well, no, actually, that's not true. So let's go ahead and go through this. So now we need to decompose our remainder with partial fractions, right? So this remainder over the denominator. So first thing, I need to factor out x cubed plus 1 uh, by the rational zeros theorem, which tells me the rational zeros theorem tells me what my possible zeros are. So it's all the multiples of the last term divided by all the multiples of the first term, right? The coefficient. So really it's just 1 over 1. So the only possible zeros I have for this are plus or minus 1. Okay. If you're not familiar with the rational zeros theorem, again, go to my pre-calculus section on polynomials, or go into the calculus 1 review stuff that I have for um, polynomials and rational functions. And all of this stuff is in there as well. Okay. So the theorem of possible zeros are plus or minus 1. Do the rational zeros theorem. So we're going to go ahead and use synthetic division here to factor this out. Okay. So if I rewrite this, this is the first factor that I'm trying. X equals -1. It goes on the outside. On the inside, it starts from the highest degree and goes down. So I have 1x cubed, 0 x squares, 0 x's, and 1 constant, right? The constant is 1, so that's where the 1 comes from. Okay. Now, in order to find these values, I'm kind of skipping some stuff here because I'm assuming this is not your first time seeing this. We always start off with 1 with a 0 under our leading 1, and we add those together. Okay. So 1 plus 0 is 1. And then the entry that I get here, I multiply times the value that is behind this wall, which is -1. 1 times -1, I put that entry under the next entry that should have nothing, which is here. So 1 times -1 is -1. 0 plus -1 is -1. -1 times -1 is 1. 0 plus 1 is 1. 1 times -1 is -1. And when I add these together, I get a 0, which is what I want. A 0 at the very, very, very end is great. If there was a number here, it means that I failed in what I'm trying to do. Now, what am I trying to do? Synthetic division allows me to evaluate a polynomial at a point, and it allows me to factor by, or divide, I guess, right? Factor by trying to pull out a factor of, in this case, x x equals -1 or x plus 1. would be the factor. So this was cube, this was square, this was just an x, and this was for just the constants. Now that we're on the next line, I disregard the end, right? So since this was starting off as cubes, down below it, this is my coefficient for squares, my coefficients for x's, and my coefficients for constants. So when I try to factor x plus 1 by, I'm sorry, x cubed plus 1 by x plus 1, I get out the result x squared minus x plus 1 times that factor that I pulled out to get the original. Okay, so let's look at what that looks like. So since our last value here is 0, it means I did a good job. I got what I wanted. That means that x equals -1 is a 0 of x cubed plus 1, meaning I can factor out if I were to zero this out, right? Add it to the other side. X plus 1 equals 0 means x plus 1 is a 0, is a factor of the polynomial x cubed plus 1, right? So that means that x plus 1 is a factor of x cubed plus 1. Again, how do I get that? We'll add 1 on both sides, and I get x plus 1 equals 0. That factor is a 0 of the polynomial. Again, look at the there if you need to. Our result at the bottom here, this 1, -1, 1, means that I have x squared negative x plus 1 with 0 remainder as the remaining polynomial from factoring x cubed plus 1 by pulling out a factor of x plus 1. So what does that mean? That means x cubed plus 1 can be written as x plus 1 times x squared minus x plus 1. Okay, so synthetic division for factoring. So that means that my original integrand, which is x squared minus this thing, once I do my long division, can also be written as x squared minus x plus 1 over x plus 1 times x squared minus x plus 1. Again, because I factored that x3 plus 1 term and wrote its equivalent term. And look what we have here. Something top and bottom, that cancels out for me, right? So I get x squared minus 1 is equal to my integrand, right? So I simplified it algebraically. So now my integrand can be factored with this equivalent integrand, which is actually much, much, much easier to factor than this. Here, this original, I can't do any u subs. I can try to do integration by parts if I try to think about this as one function times another function, where one function is a polynomial and the other function is a rational function. This has a denominator. Then I try to integrate one and differentiate the other until I get to 0 using the table method. I can do that. It might take a very long time. And the cleanup at the end would be horrendous, right? After multiplying everything out and then trying to add and subtract them all together, you'll be adding several rational functions together. Okay. So I'm here. This first term is very easy to integrate once I distribute this integral sign, right? And this 1 over x plus 1 is actually very easy to integrate as well. I just let u equal x plus 1. And when I differentiate u, I just get du because the 1 goes away. Or I'm sorry, when I get du, and x plus 1, when I differentiate it, just turns into dx. So it's very easy uh, to use the u substitution here. And then you just have 1 over u, which the integral of that is natural log. And then you can substitute this x plus 1 back. So at this point, you should be familiar with that because we've been doing it all over the place. So I talked you through it. If you want to do a little bit of side work to verify this, just use a u substitution where x plus 1 is your u. Okay. My x squared term turns into 1/3 x cubed. Okay. And so I integrate this and I get this result out. So another example, let's integrate x cubed plus 6x minus 2 over x to the fourth plus 6x squared. So notice that right away, the denominator is a higher degree than the numerator. So I do not need to do any long division. That's great. So I do need to factor the denominator. So I can use synthetic division for that. I can give it the good old 1-2 shot for just regular factoring and see what I get. So luckily, this is an easy one to try to factor. Common term is x squared. So I just pull out x squared. However, I cannot factor out the interior anymore, right? Um, and so now this is case two and case three. I have one linear factor, x squared, of multiplicity, and then I have a quadratic factor, right? Since this is degree two, that is prime. I can't factor this anymore. So I have one prime quadratic factor, which is three, and I have a linear factor of multiplicity. That multiplicity is two because it is an x squared term. Okay. So I want to rewrite this in the form of what my decomposition will look like. So x cubed plus 6x minus 2. I factor the denominator now, x squared plus 6. Notice this does not have the integrand sign because I'm not integrating. I'm going to decompose this fraction um, so that it's easier for me to integrate. So I have a over x plus b over x squared. So that comes from my x squared term. Remember when it's multiplicity, you write 1 and then you keep writing it again at 1 power higher until you get to the power that's there. So since there's only x squared, I start with x. And then the next one is where I end, which is x squared. So this is just coming from this first term. I have an a on top and a b on top. My quadratic factor is prime, so it's x squared plus 6. So the generic form of that was a1x plus b1, but I've already got terms here, so I'm just going to go a, b, c, d, e, yada, 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 until I run out of letters. Okay, it's a lot easier to keep track of that way. So they're letters we're familiar with. So I have a linear factor on top of my prime quadratic. That's basically what that looks like. I don't know what the values of a, b, c, and d are. That's what I'm trying to find. Once I have those, then I can rewrite this integrand, and then I can integrate this integrand, right? Rather than this one that's too hard for me to do. So I'm going to clear denominators. So maybe you're saying, what does that mean? I'm going to take the denominator in its factored form on the left side, right? When I was in algebra classes, this is one of my favorite problems that I used to give to people, right? So if you have ever taken algebra from me, then you'll be familiar with this. I will multiply the numerator here times the denominator. And I'm going to multiply this numerator times this entire denominator, this numerator times the entire denominator, this numerator times the entire denominator. Basically, what I'm doing is I'm multiplying this on the left-hand side of the equation and the right side of the equation. Okay, so I'm going to apply each term by that denominator. So obviously, it should cancel out with the left side, right? Because if I'm multiplying the numerator times this term, it cancels out with the denominator. When I multiply this times the first term on the right, the only thing that cancels is one of the x's. So what I'm left with is an x times an x squared plus 6. Okay. On the b term, this entire x squared term cancels, and I'm left with this x squared plus 6. And when I multiply this on the last term, the x squared term stays, but the x squared plus 6 goes away. Okay. So what I'm going to do now is I am going to multiply this all out. That'll be the easiest thing to do. So this will turn into ax cubed plus 6x, right? This will be bx squared plus 6b, and this will be cx cubed plus dx squared. Now I am going to equate similar terms, okay? Meaning there's only one x cubed here. There's an a plus a c x cubed, okay? So x cubed, the only way to equal this x cubed is to add all the x cubes on this side, since they're equal. right? So this 1x cubed has to be equal to the ax cubes plus 6x cubes. 6x, sorry, I'm skipping one. There's no x squares on this side, but I do have two x squares over here. So bx squared plus dx squared has to equal 0. Okay. For the x's, 6ax has to equal 6x. Okay. That's the only term here that has only one x. And for the constants, the only one is the 6b. So 6b has to be equal to -2. So from here, this is the system of equations that I want to solve for. I want to know what A is, B is, C, D, right? I need to know what they are. Here, it's very easy to see. Before we even do this, what we can do is let's get rid of these x's because these x's are confusing me. If I take this first equation and I divide both sides by x cubed, all of the x cubes go away. And I'm left with just 1 equals A plus C if I were to divide by all the x cubes. The way that I think about it is instead of dividing by all of them, I'm just going to take them away. Same thing. One of these is equal to A plus C of these. They're all the same thing. So I'm just trying to find out the values. I don't need the variables. Same thing here. B plus D is going to equal 0. Here, I don't need the x's. 6 is 6a. And here, -2 is 6b. There's no x's already, so I don't have to worry about that. Using this bottom one, it's very easy to see that a is equal to 1, right? 6 times something. 6 times something. It has to be 1, right? Another way to find that, obviously, is to divide both sides by 6. Here, if I want to get b alone, I divide both sides by 6. It's very easy to see that b is -1/3. Okay, so I got a is 1. If I come up here and I were to plug in 1, I would have 1 is equal to 1 plus something. Well, that means that that something has to be nothing then, right? Because a is already 1. B, you can look here and get -1/3. And now we can use these two things to figure out D. I know B is -1/3. For these to add together and get 0, that means D would have to be just a positive value, opposite sign of B. So since this is negative, D is just the same thing but positive. Okay, very easy for us to find. But we are not done, right? So there's a lot of times where you can be like, oh, I did some work and I got to an answer, I'm done. You have to remember, I'm not just trying to find A, B, C, and D. That's not what I'm trying to do. I need to take these values and I need to plug them back in here. Then I have an equivalent form of my integral that's easier to integrate, and then I have to integrate. So I have to do this in order to get to the point to integrate. So I know A is 1, so I would replace that with 1. I know B is -1/3, so I'd place this as -1/3. C is 0, so there's no x term here, and D is a +1/3. Okay, so remember, you never put fractions inside of fractions, so we can simplify that a lot easier, right? So A is 1 over x. If there's a fraction here, the denominator here gets to just move down and be with its other buddies downstairs. Same thing here, right? So I write this as 1 over 3x squared. And here, remember D was 1/3, so that 3 moves down to be downstairs with this x squared plus 6. So now I have an equivalent for it, right? If you needed to check your work, you would add these all together and make sure that you come out with this original uh, rational function. Okay, that's how you would check to see if you're on the right path. If I want to integrate this function, I got to integrate the equivalent function that I just created. Okay, I can distribute this natural log over, or I'm sorry, this integral over, which makes things a lot easier. This first one is natural log. Okay, this is x to the -2. So remember, you just go up by 1 and multiply it by the reciprocal. So I have -1/3 times a negative 1, -1, basically. And then this turns into 1 over x, right? X to the -1 power. This one, I can't just go right for it, right? But, so I'll leave it alone, to be honest with you. for right now. So I integrated two, and now I'm just going to work on this last one. So remember what we did last section, right? It's something squared plus a number. So that's very reminiscent of something for a trig sub. I can do a u substitution. U equals x squared plus 6 doesn't do anything for me, right? I can't complete the square here. There's no b term for me to complete the square. Um, so this is very similar to a trig sub where I'm adding both things. So I would use the square root of the a term, because remember this is like an a squared, and I multiply that times the tan theta. So I would use the substitution, x equals a tan theta, where this is x squared plus an a squared. I don't have a square root here, but that's fine. We saw before, we don't always need the square root. We just need to have something of this form in order to try to use it. So when I differentiate both sides implicitly, I get dx, okay? The tangent turns into secant squared, and then I differentiate the inner theta as d theta, right? The root 6 doesn't do anything. It's just a constant value, right? So I have my x substitution. I have a new dx. I'm just going to substitute everything into that interval, right? So for this one portion, um, dx then becomes root 6 secant squared theta d theta, and x squared then turns into root 6 squared, so that's 6, and then tan theta is tan squared theta. Okay, so now I have a much more convoluted problem at this point, right? But once we start doing our work, things cancel out, right? I'm going to pull out this common value of 6. I know that this is just secant squared, okay? So if you notice here, you might say, how the hell do you get this? I, just to be fancy, unrationalized the numerator, right? So I brought I multiplied by root 6 over 6, and in doing so, the numerator becomes 6, the denominator becomes root 6, and so the numerator, as it's a regular 6, and this denominator 6, just get to cancel. So I unrationalized the numerator just so I can cancel out the 6 on the bottom, okay? I could have just multiplied it through and wrote it as root 6 over 18. That's fine also, okay? But I wanted to look a little bit simpler, so I um, rationalized the numerator. We know this cancels out, okay? And so now when I integrate, this just turns into 1 over 3 root 6 theta. Okay? I need to solve for theta, so remember, I take my original substitution and I solve for theta. So I would divide by root 6 on both sides and then take tan inverse. So theta is tan inverse x over root 6. So putting all together, I have my natural log of x, 1 over 3x. Here, I went ahead and re-rationalized the denominator. And so it's 1 over 18 root 6 times theta, which is tan inverse. Um, and again, I rationalize this. So that's root 6 over 6. And so it's a little bit cleaner when you write your variables in front of the root instead of the root in front of your variables. There's no instance here because I don't do that. Plus my constant. Okay. So there was a little bit involved in this one. We had a lot of stuff. We had a natural log. We had to use a trig sub, and we had a very standard type of integral. And all of that came from the decomposition because trying to solve this as it is would have been impossible, right? So we had to decompose it into smaller pieces. We broke it down into smaller, more manageable pieces, okay? This was just natural log. This is just a power function. This one I needed to use a trig sub. So I did that, and there's our work. So as you can see, the problems are starting to get longer and longer and longer, and that is how calculus works. So let's go ahead and move on to our next example. Let's integrate the square root of 1 plus square root of x over x. So if you're looking at this, you're like, well, I don't know really what the degree is of the numerator, but I know it's not more than the denominator. It's also not a polynomial, so how am I going to factor anything? How do I factor just an x, right? It's not gonna, I can't do synthetic division or long division here. It doesn't, none of that's gonna work, right? This is all very convoluted. Well, sometimes we have to take a step back and just approach the integral as an integral, right? Instead of saying, hey, this is in the partial fractions decomposition section, what's the partial decomp gonna be? Maybe that's not the first step. If I see this, the first thing to me would be to make a u substitution. I would probably start with 1 plus square root of x and try and see how that works. So I went ahead and did it, and it works better if I make the entire numerator um, the substitution rather than just the inside part, because then it gets a little bit messy and it's easy to hit a wall, right? So I came back and then I tried to solve it using the entire numerator instead, and it worked much better, right? So I'm gonna go ahead and play with the substitution a little bit. I'm gonna square both sides to make it a little bit easier to deal with. Um, and then from here, I'm going to go ahead and isolate the square root x because that's really what's kind of giving me the problems in here, right? So for the square root x, I have u squared minus 1. So notice what happens if I were to plug this in right now, I would have 1 plus u squared minus 1. And everything would be left over, would go away, except for this u squared, which would then get square rooted, which would turn into just a u. So this actually is very, very helpful to me right now, right? If I go ahead and square this, then I have the substitution I may need for the denominator. So from here, let's go ahead and differentiate both sides. Okay. Differentiating this, you get the chain rule, so you get the 2 on the outside with the inside unchanged, and then you differentiate the inside on the outside. So my dx gets differentiated to the differential d of x, right? And this u on the inside gets differentiated into this du, the differential of u. So my d of x is this long thing, right? So now I have a value for x in terms of u. I have something for, I mean, I could just put u for the entire numerator, and that would be fine, right? Um, so let's go ahead and make our substitution. Okay. So if I'm solving for dx, just simplifying here, right? The 2 and the 2 is the u, and then u squared minus 1. So if I take this, for d of x, I have 4u, u squared minus 1. Okay. For this top part, 1 plus square root of x, all under square root of x, is just a u. Okay. And for x, I have u squared minus 1 squared. And now look at it. Now it is all powers of u. If I multiply these out and I expand everything, it's a polynomial on top, polynomial on bottom. So it may not have looked like partial fractions was correct the first time, but after playing with it, you can see here that this turns into a partial fractions problem. So this u squared minus 1 on top cancels with one of them on bottom. And then I have a 4u squared on top. I can pull out the 4, right? And here, we're running into a very similar problem. This is the same degree, but u squared minus 1 factors very nicely. Okay. So we'll go ahead and do our long division here. So what do I do in order to make these the same? Well, nothing. They are the same. So it would just be a 1. Okay. So when I subtract these two, right, I get u squared minus u squared, and then 0 minus a negative 1 is plus 1. So this is my remainder now. Okay. This is my remainder. And so I get 1 plus remainder over what I'm dividing by. This factors very nicely, okay, into u plus 1, u minus 1. They're distinct linear factors, right? So the decomp looks like just a and b. And so now that I have this relationship for the part that I'm trying to do the partial fractions on, I multiply everything times this denominator, which for the left-hand side will cancel out. On the right-hand side, I will have the u plus ones will cancel out, and I'm left with u minus 1. For the b side, the u minus 1 will cancel out, and I'll be left with b plus 1. Right? When I multiply these out, I get a u plus bu equals nothing. There's no u's on the other side. For the constants, I'll get a negative a plus b equals 1. So a was negative, b was positive. I can just go ahead and move those around. B minus a instead of a, uh, sorry, negative a plus b. Just swap the order. And so this is the system that I want to solve. A plus b is 0. Uh, b minus a is 1. So here it's very clear. A is negative b, right? A plus b are the same value but negative. So if you put that substitution here, if a is the same as negative b, I get b plus b, right, is 1 or 2b. So then that means that b has to be half, right? And a is just a negative value of that, so it's negative half. You should be able to do that on your own. Maybe not as fast as I talk through it, but that's not a hard system to solve. So a is negative 1/2, b is 1/2. So I do the same thing. 1 and a 2 on the bottom, 1 and a 2 on the bottom. Make sure you keep the signs. So this 1 plus 1 over u squared minus 1 will decompose to 1 over 1 minus 2 times u plus 1 plus 1 over 2 times u minus 1, right? So I could multiply this 2 out, so it's 2u plus 2. It doesn't matter if you factor it or keep it like this. But when I distribute this integral sign, I can move those 1/2 to the outside. So I'll keep it like this. So the 1 turns into u here using, let's say, I don't know, a VW substitution. You should get natural log of u plus 1 times 2. Same thing here. You should get plus 2 natural log u minus 1, and then that constant of integration. And we're not done yet because we're in u. So we got to go all the way back and be like, oh, this was what u was, right? I got to go back into the world of x. So I can simplify a little bit here first, I guess, right? Using the rules of natural logs. So I just put u1 over u plus 1. I could substitute u first and then do that. It doesn't really matter at this point. Obviously, working with u algebraically is going to be easier and cleaner. But the next step is, again, to substitute that square root 1 plus root x. So 4u turns into 4, and then the value of u, right? Remember, this was u minus 1 on top, u plus 1 on bottom, plus the constant of integration. That is my partial fraction decomposition. I'll see you guys on the next video.